How Earth creates its brilliant daylight. Consider how Earth transforms a single star's light into the brilliant daylight that illuminates our world from horizon to horizon. The sun represents just one ordinary star among the countless billions scattered throughout the galaxy, yet during daytime hours it manages to flood our entire planet with radiant brightness. This remarkable transformation occurs not because our star possesses any special properties compared to distant suns, but because Earth possesses something that space completely lacks, an atmosphere packed with particles that redirect and amplify the incoming solar radiation. Our atmosphere contains approximately 78% nitrogen, 21% oxygen, and traces of other gases, along with countless microscopic particles including dust, water droplets, and aerosols suspended throughout the air column. These components create a dense medium that fundamentally alters how light behaves when it enters our atmospheric envelope. Every photon arriving from the sun encounters billions of these tiny obstacles during its journey through the air, causing the light to bounce and scatter in multiple directions rather than traveling in straight lines. Rayleigh scattering governs this atmospheric light redirection process. When sunlight encounters gas molecules and particles smaller than the wavelength of visible light, these tiny objects act as microscopic mirrors that deflect the incoming radiation. The effectiveness of this scattering depends directly on the wavelength of the light involved. Shorter wavelengths experience much stronger scattering than longer wavelengths, with blue light scattered approximately 10 times more effectively than red light. This wavelength-dependent scattering explains why our daytime sky appears blue rather than the white color of direct sunlight. Blue photons with wavelengths around 450 nanometers get bounced around the atmosphere so extensively that they seem to arrive from every direction simultaneously. Meanwhile, red photons with wavelengths near 650 nanometers pass through the atmosphere with minimal deflection, allowing them to maintain their original directional properties. The result creates the familiar blue dome that surrounds us during daylight hours. The atmosphere essentially functions as a vast network of light redistributors. Each gas molecule and particle acts as a tiny relay station that captures incoming solar radiation and broadcasts it in random directions. This process transforms the sun's parallel beam of light into a diffuse glow that illuminates the entire sky hemisphere. Without this scattering mechanism, we would see only a brilliant white disk of the sun against a completely black background, similar to what astronauts observe from space. Atmospheric particles redirect light with remarkable efficiency. A single photon might encounter hundreds of scattering events during its passage through the air column, getting bounced from molecule to molecule before finally reaching our eyes. This multiple scattering creates the soft, even illumination that characterizes terrestrial daylight. The light arriving at any location on Earth's surface includes both direct radiation from the sun and scattered radiation from all other directions, combining to produce the bright conditions we experience. The thickness of our atmospheric layer determines how extensively this scattering occurs. During midday, when the sun reaches its highest position, sunlight travels through the minimum amount of atmosphere, resulting in intense blue sky conditions. As the sun approaches the horizon during sunrise and sunset, light must traverse increasingly thick atmospheric layers. This extended path allows more scattering opportunities, causing shorter wavelengths to get deflected away while longer red and orange wavelengths continue toward the observer. Astronauts orbiting Earth witness a dramatically different visual environment that reveals how unusual our atmospheric light amplification really is. From space, the sun appears as an intensely bright point source against the absolute blackness of the cosmic void. Even with the sun shining directly on their spacecraft, astronauts see no diffuse sky glow whatsoever. The absence of atmospheric particles means that light travels in perfectly straight lines, creating stark contrasts between illuminated and shadowed regions. This atmospheric amplification effect theoretically should apply to starlight as well as sunlight. Every star in the night sky emits photons that enter our atmosphere and encounter the same gas molecules and particles that scatter solar radiation. The light from Sirius, Vega, and countless other stars should undergo Rayleigh scattering, just like sunlight does, creating diffuse glows that brighten the night sky. Yet, despite containing the same scattering mechanisms that create brilliant daylight, our atmosphere fails to transform starlight into significant sky brightness. Even on the clearest nights, far from artificial illumination, the scattered starlight contributes only a faint glow that remains barely detectable to human vision. This dramatic difference between the atmosphere's treatment of sunlight versus starlight hints at fundamental distinctions between our local star and the distant stellar population. The intensity difference between sunlight and starlight provides the crucial factor explaining this atmospheric amplification discrepancy. Our sun delivers approximately 1,360 watts of energy per square meter to Earth's upper atmosphere, creating an enormous flux of photons available for scattering. In contrast, even the brightest stars deliver less than 1/1,000,000th of this energy flux, providing far fewer photons for the atmospheric scattering process to redistribute. Our protective atmospheric envelope creates a localized bubble of enhanced brightness around Earth by capturing and redistributing the intense radiation from our nearby star. This process transforms what would otherwise be a single brilliant point of light into the diffuse, comfortable illumination that sustains life on our planet. However, this same atmosphere cannot perform similar brightening magic with the incredibly faint light arriving from distant stars scattered throughout space. The brilliant blue sky that surrounds us represents an artificial enhancement created by our planet's gaseous envelope, but this raises a profound question about what happens to light when it encounters the vast emptiness between the stars. The shocking emptiness of space. Space operates under completely different rules than our familiar atmospheric environment. The vacuum between stars contains fewer than 1 atom per cubic centimeter, creating conditions so empty that light rays travel for billions of years without encountering a single particle capable of redirecting their path. This extreme emptiness fundamentally changes how illumination behaves compared to the dense conditions that create Earth's bright daylight. The interstellar medium represents the closest thing to a perfect vacuum that exists in nature. Between stellar regions, particle density drops to levels that terrestrial laboratories struggle to replicate even with advanced vacuum technology. A cubic meter of space might contain fewer particles than exist in a single breath of Earth's atmosphere. This sparse distribution means that starlight encounters virtually no obstacles during its passage through the cosmic environment. Without scattering particles, light maintains its original directional properties throughout its journey across space. Photons travel in perfectly straight lines from their stellar sources without experiencing the random deflections that create atmospheric brightness on Earth. Each light ray maintains its precise trajectory, carrying energy in a narrow beam that only becomes visible when it directly enters an observer's eye or strikes a physical surface. The space between these light beams remains completely dark because no particles exist to redirect the energy toward other viewing angles. This directional nature of unscattered light explains why astronauts see only pinpoints of stellar brightness against an otherwise black background. Even when surrounded by intense starlight streaming in all directions, the space around them appears dark because their eyes detect only the photons traveling directly toward them. The countless light rays passing nearby remain invisible because nothing deflects them into the astronaut's line of sight. The contrast between Earth's atmospheric density and space's emptiness becomes apparent when comparing their particle concentrations. Our planet's atmosphere contains approximately 2.5 quintillion molecules per cubic centimeter at sea level, creating a dense medium that interacts extensively with incoming radiation. The interstellar medium averages less than 1 particle per cubic centimeter across most of its volume. This represents a density difference of more than 24 orders of magnitude, explaining why atmospheric scattering creates bright skies while space remains dark. Even regions that astronomers consider relatively dense still contain far too few particles to generate significant light scattering. The densest molecular clouds in the galaxy might reach concentrations of several million particles per cubic centimeter, which sounds impressive until compared to atmospheric densities. These supposedly dense cosmic regions still contain fewer particles than exist in the best laboratory vacuums on Earth, making them incapable of producing the scattering effects that brighten terrestrial skies. The concept that darkness represents the absence of scattering rather than the absence of light fundamentally changes how we understand cosmic illumination. Space contains enormous quantities of electromagnetic radiation streaming in all directions from countless stellar sources. This energy fills the cosmic volume, carrying power levels that would overwhelm any observer if concentrated into visible form. However, without particles to redirect and scatter this radiation, it remains invisible to anyone not positioned directly in its path. Consider the light streaming past Earth from distant galaxies at this very moment. Trillions of photons carry energy through the space around our planet, traveling on trajectories that will carry them to other regions of the universe. These light rays pass invisibly through the solar system because no scattering medium exists to make them visible. Only the tiny fraction of cosmic light that happens to travel directly toward Earth becomes detectable, while the vast majority continues its journey unseen through the empty space between celestial objects. This explains why adding more stars to the universe cannot solve the darkness problem through simple multiplication. Each additional star contributes its own beam of directed light, but these beams travel in straight lines without illuminating the space between them. A trillion stars produce a trillion separate light beams, but the dark regions between those beams remain just as dark as before. The emptiness of space ensures that increased stellar populations create more points of light rather than diffuse cosmic brightness. Cosmic dust plays a particularly important role in the limited scattering that does occur in space. These microscopic solid particles, composed primarily of silicates and carbon compounds, interact more effectively with light than individual gas molecules. Dust grains can absorb starlight and